Okay, so welcome everybody to this very first SPD seminar in this semester. So our first speaker in the spring is Yanghui Liu from Baruch College. Yanghui did his PhD in 2006 at the University of Kansas.
2016.
2016, sorry, 2016. I'm so sorry. And from 2016 to 2019, he then went to Purdue University as a visiting assistant professor. And since 2020, he's an assistant professor at Baruch College. And we're very happy that you're here today and give a seminar talk about numerical approximations for rough differential equations.
Okay, thank you, Carsten, for invitation. Could I confirm if everyone can see my screen?
Yes, I think it looks good.
All right. So the talk will have 3 parts. I will start with the introduction of the numerical approximation for the rough differential equations. And in the second part, I will derive upper bound for upper bound estimates for the Euler scheme. And in the end, I will talk about the integrability. The integrability will be used to derive the Malliavin derivative. Okay, let's start with the introduction. Let us start with the stochastic differential equation, dy equals v of y dx. We can also write this in the integral form, yt equals y0 plus the integral of v of y dx from 0 to t. So here the driving process x takes the values in Rm. And here v is a deterministic function. We know that in the classical stochastic analysis, the SDE is solved when x is a Stedman martingale. The rough path theory provides a pathwise interpretation of the SDE and allows to consider a wider range of continuous driving processes. This was studied by the Lyons paper in 1998. Let x equal to x1 up to xd to be a continuous centered Gaussian process with IID components. The covariance function of the process x is defined as follows. We denote it by R of st, which is equal to the expectation of x js times xjt. So this is our definition of the covariance function. We know that R has a finite 2D row variation for row greater or equal to 1 and less than 2. And and then x gives rise to a beta rough path. And the rough path we denote by x, bold x, which is equal to x1, x2, x3, provided beta is below 1/2 row. And with this assumption, the SD is well defined. The fractional Brownian motion is the prototype of the Gaussian process. So in the following, let us define the fractional Brownian motion. So here's the definition of the fractional Brownian motion. H is a number between 0 and 1. And a fractional Brownian motion with Hurst parameter h is a centered continuous Gaussian process with covariance function given by 1/2 times s to the 2h plus t to the 2h minus t minus s to the 2h. So when h is equal to 1, this fractional Brownian motion is just the standard Brownian motion. So there are some important application of a fractional Brownian motion recently in finance, statistical mechanics, and also hydrodynamics. Here are some simulations of the fractional Brownian motion. The first one is when, remember, the fractional Brownian motion has a parameter h So the first picture is when h equal to 0.7, and the second is when h equal to 0.5, and the last picture when h equal to 0.3. Remember, when h is equal to 0.5, this is the Brownian motion, the sample path of the Brownian motion. And as you can see that the path gets rougher when h is smaller. Okay, let's come back to the differential equation. dy equals v of y db. Here we use the fractional Brownian motion to be our driving process. As we have mentioned that the SD is well defined if we have a proper assumption on the Gaussian process. So specify this condition to the fractional Brownian motion. We have that when h is greater than 1/4, there exists a beta rough path for B. Whenever beta is greater than 1/2h. And in this case, the SD is well defined. Now let us take a uniform partition over the time interval 0 to t. And we denote the partition by t0, t1 up to tm. The Euler scheme is defined as the delta yn from tk to tk plus 1 equal to v of yn tk times delta b tk tk plus 1. So here, delta b tk tk plus 1 is equal to btk plus 1 minus btk. That is the increment for b. And delta yn is the notation for the increment of yn. And so if I compare this Euler scheme to the equation, you can see that the Euler scheme is just the linearization of the equation. So here are some simulations for the Euler scheme. In the first picture is the Brownian motion case when h equal to 1/2. The blue curve is the solution curve, and the red curve is generated by the Euler scheme. And then we can see that the Euler scheme follows the solution closely. And the classical results tells us that the strong rate for the Euler scheme in the Brownian motion case is 1/2. So it means that means the error process is bounded by n to the minus 1/2 times the constant. And the weak convergence is 1. So the error process is bounded by 1/n. Now let's move to the case when h equal to 0.55. That is the fractional Brownian motion case. The blue curve is still the solution, and the red curve is generated still by the Euler scheme. And you might believe me that this curve has a very different, behaves very differently comparing to the Brownian motion case. So this was quite surprising. So here's our explanation of this behavior. So the limit as h approaches 1/2 of the SDE corresponds to Stochastic type equation. And on the other hand, the naive Euler scheme, the Euler scheme we just defined, is the extension of the Euler scheme for Ito type equation. And we know that to transform Ito type equation to Stochastic type equation, there will be a correction term. So these 2 points, from these 2 points, we can see that when h gets closer and closer to 1/2, we will have a much worse convergence for the Euler scheme. Okay, so this is our explanation why this happens. And based on this observation, we have introduced the following new scheme. This new scheme, the only difference is this, the term in blue. This is the new term we have added. This is a modified Euler scheme. The first part of this term is just the partial derivative of the function v times v. And the second part is delta to h. This is a deterministic term. Delta is equal to the step size, t over n. And so an intuition of this term is that if you take h to be 1/2, so let's take h to be 1/2, and this becomes delta. And then this term is exactly the correction term between the Stratonovich equation and the Ito equation. Okay, so let me also mention that if we replace this delta to h by the product of the increment of b, we will get the implementable scheme. The implementable scheme has been considered in these two papers by Deya, Neunkirch, and Tyndall in 2011, and Fritz Riedel in 2014. Okay, so once we have introduced the scheme, we want to simulate the scheme, right? So here is the simulation, the blue curve. So here h is 0.55. The blue curve is the solution curve, and the red curve is still the classical Euler scheme, the naive Euler scheme. And as you see, the approximation is not good enough. It's kind of going away from the solution. And if you look closer, there's a black curve. The black curve is following along the solution curve. The black curve is generated by our modified Euler scheme. And so besides this simulation, we have also several other evidence showing that this new scheme is the authentic Euler scheme. Okay, so here are some results about the Euler scheme. When h is greater than 1/3, the strong rate of this new scheme is n to the 1/2 minus 2h. And for example, if you take h to be 1/2, you will recover the classical result for the Euler scheme for Ito equation. When h is greater than 1/2, we also have the weak convergence result, and the rate is n to the -1, which does not depend on h. I'd like to say a few more words about the proof. So the main idea, a key step for the proof, is to observe that the error process y minus yn can be decomposed into two parts. The first part is a weighted sum, and the second part is the r. R is the remainder term. Okay, so in this summation, the summation will be the dominating term. It will dominate the error. And in this summation, this capital F, this is our weight process. And the second term, I will denote it by Hn. And this is a double square root integral. Okay. So once we have this decomposition, the weighted sum, this part is then dealt with based on the transfer principle in our paper in 2019. Let me mention that this kind of a decomposition is true for any time discretized numerical approximation in general. So, so for any numerical, time discretized numerical approximations, we can always decompose the error into a weighted sum plus a remainder term. Okay. So let me also say a word about the transfer principle I just mentioned. The transfer principle was for the weighted sum. In order to bound the weighted sum, here I just write summation of ftk. Remember, f is the weight process times hn. In our example, in the Euler scheme case, hn is a double integral. In order to bound this quantity, or in order to find the limit theorem for this quantity, the transfer principle tells us that it suffices to look at the following elementary sums. The first one is the sum is kind of like the unweighted sum. So you see, I take away the weight f, and the other terms are weighted sum, but they are simpler than our original weighted sum, because the weight are the weight are just the signature of the fractional point motion. And here's L. Here, this L is an integer depending on B and Hn. So you don't need to consider infinite sequence, infinite many sums. You don't need to consider finite many. And again, I just mentioned that the weight, those are weighted sums, but the weight processes are in finite chaos. They're just the signature of the fractional point motion, so they are finite chaos. And so they're much easier to deal with. Okay, so now let us talk about the upper bound estimate. So I will only consider the scalar case just for simplicity. I will start by introduce the following process, QST. This is the summation of the B squared. So if in the scalar case, this is just the, the square of the increment times 1/2, minus 1/2 times delta to 2h. So let me explain why I introduced this. So we will consider the couple BQ instead of B as the driving process for the Euler scheme. And therefore we need to consider the new control function. The control function denoted by W. It has two parts. The first part is the P variation of the fractional point motion. And the second part is the P/2 variation for the process Q. And I have hidden the technical details just for simplicity. Okay, so let's denote Z to be the Malliavin derivative, dHYNT. Here Yn is the Euler scheme, and the H is a vector in the Cameron-Martin space of B. Now the proof for the upper bound of this Malliavin derivative and also higher order derivatives is based on a discrete serial lemma. So once we have set up the driving processes for the discrete equation and also the control function, we are ready to apply the discrete serial lemma. And in the following, I will mention some ingredients of the proof. We first need to introduce a sequence over the time interval 0 to t. So let me fix a constant alpha. And for a given Sj, Sj plus 1 is defined as the maximum, the largest t that is greater than Tj, such that WSJ to t is less or equal to alpha. And we also assume that the maximum of empty set is Sj plus delta, so that we don't, stay at the same value if the set is empty. We still move on. We still take a step ahead, forward. Okay, so in Cass Literal Lines paper, this sequence, so this sequence was already used in this paper, and it's called the greedy sequence in the paper. And in their case, they consider continuous equation, and therefore they will always have this inequality, and so they don't need to worry about empty set. And in our case, it's possible that the W of Sj to Sj plus 1 is greater than alpha. And therefore, we have to make this assumption that maximum empty is equal to Sj plus delta, so that Sj plus 1 is always different from Sj. Okay. Now, so for this greedy sequence, we have 3 situations. This is different from the continuous case. We have the first case when Wsj to Sj plus 1 is almost equal, close to alpha. That is the regular case. And we may also have the case when the step is very short. So this is a small step. That's when it is much smaller than alpha. And the last case is the case when the set is empty. We already mentioned here. If the set is empty, it's possible that Wsj to Sj plus 1 is much bigger than alpha. Okay, so we just categorize the Sj into 3 groups. Okay, another ingredient in the proof is a chain rule. In the left-hand side of this chain rule is the higher derivative, a higher Malliavin derivative for f of capital F. So you might expect that if you differentiate this f of capital F, you will end up quantities like this. So you see, this is a partial derivative for f, and then you will get the Malliavin derivatives for capital F. The trouble here is how to get the precise equation. So it turns out we need to, so in order to characterize the index, we need a directed tree. So here this AN is a directed tree, and I is a branch in this directed tree. And this L1, L2 up to L alpha I depends on I. Okay, so let me just mention one example of this directed tree. So when capital N is equal to 4, this is what this tree looks like. Okay. All right. So here's our upper bound. We can bound the p variation of z by a constant times the control function from s to t to the exponent 1 over p times 3 quantities m0, m1, m2. So m0 corresponds to small steps. Remember, S0 is for Sj that has a median step, and M1 is corresponding to steps with Sj with small steps, and then S2 is for Sj with large steps. So that's why we have 3 quantities here. And this is our upper bound. And we can use the Enhamas idea. in order to get a similar bound for the Malliavin derivative in the H norm.
Yanghui, I have a question. So what's the difference between the things that you multiply in M0 and in M1? Aren't they the same?
0 is when the step is median step is close to alpha. So let me go back to the definition. Yeah, so M0 corresponds to Sj belonging to this category. That's when it is close to alpha. And it's possible that the step is very small. So we need another group when it is much less than alpha. Yeah, so in the continuous case, in Cass literal lines paper, they only encounter small step in the last step. So most of their steps are equal to alpha because the equation is continuous. And they only have one term that is smaller than alpha, which is the last term.
But you need to distinguish that, because I think when you take the product, in the end, you multiply the same thing. So my question is really, can you just take the union of S0 and S1? So why do you need to have two different groups?
Yeah, very good question. So if I go, let me go back here. So later in the last part, I will quickly explain how I show the integrability of M0. So I will apply the Baruch inequality to bound M0. But this proof only works when the step is a medium size, not big, not small. There's a medium size. So that's why I take this out, M0, I take this out. Yeah, thanks for the question. So
thank you.
If you take this out, it turns out it doesn't harm. The reason it doesn't make more trouble is because this M0 turns out to be related to M2. So each time you have a small step, you will follow a big step. So M1 and M2 are related. So in the end, we only need to show the integrability for M0 and M2, and M1 will be a consequence of integrability for M2. So even though I get one more term, but it doesn't really make more trouble here. Okay, yeah, that's exactly what I'm going to show next. So in order to show the Malliavin derivative, Malliavin differentiability for Yn, it suffices to show the integrability of these three quantities. Okay, let's talk about the integrability. Once we have integrability, we will get the uniform bound, uniform integrability for the Malliavin derivative. And yeah, I should mention that the motivation for showing the integrability of the Malliavin derivative is that it is a key step for weak convergence and also for the density convergence, which is an ongoing project. Okay, so let's recall that M0 is this quantity. It is the product for Sj belonging to S0, which is the median steps. So let me just only mention that the integrability is obtained based on the Baruch inequality. And the main argument is similar to Cass literal lines paper. So in our case, the driving process is the BQ couple. So we have many new troubles there, but I will not get into details for that. I will, so what I'm gonna do is I'm gonna focus on the integrability for M2. And I will consider a simplified version of M2. And so it's simplified, but the proof is almost identical to M2. All right, so so we introduced this simplified version. We call it M3, which is the product of the increment of B plus 1. And here, TK is the partition point from S3. S3 is TK such that the increment squared is greater than alpha. So this is, so our goal now is to show that this is integrable. So this is a very interesting problem. So let's do some quick computation. So let's calculate the expectation of the S3. So first, let's write this S3 as the summation of indicated functions. So we can always do that. The number of points in S3 is equal to the summation of this indicated function. And now let's take the expectation. And here we need to use the Chebyshev inequality, and we get this bound. And you can see this bound is much smaller than 1. And so what does that mean? It means that in this product, most likely there's no term, it's empty set. There's no term in it. So we have a very good chance to get the integrability. So here's our plan. We will need to derive a tail estimate for S3. And the idea is to relate this guy S3 to a Gaussian functional in the finite chaos. Okay. So let's recall that the cardinality of S3 is equal to the summation of the indicated functions. Now, let us fix a constant integer m, and we define a subset of the partition. We denote by um. And let's define yum, which is very similar to S3, except that tk belongs to um. Okay. And then it's easy to see that we have the following inclusion. Whenever the S3 equal to m, we can always find a subset such that yum equals m. Okay, so remember our goal is to get to estimate this event. And now we have this inclusion, so we are going to focus on y. Okay, so let's do some estimates for the integrated function. Remember, we want to get a bound in the finite chaos. So first step, we can bound this integrated function by 1 over alpha times the square of the increment times the integrated function. So this is obviously true because the multiple is greater than 1. And next, we can subtract this increment squared by delta to 2h, and then we can take away the integrated function. So now you see I can bound this integrated function by a term in the second chaos. So this guy is in the second chaos. Okay. Now we have used um, which is a subset of the partition. And we can also introduce x. So this is a summation for tk from um. And now we use the bound of the indicated function to define x. And then we can bound y by x. So this is the definition for y, and this is the definition for x. And this inequality is true because of this inequality right here. Okay, so we get yum less or equal to xum, and xum is in the second chaos. Okay. All right. So far we have got the inclusion, and we have got the inequality, y less than x. And now we are ready to now we combine, put them together. We get that this event is included in the union of x greater or equal to m. So in order to get the tail estimate for S3, we just need to bound the right-hand side, bound the probability of the right-hand side. And this is a event for the chaos, for functional in the second chaos. Okay, so this is what we got after we take the probability. And now let us focus on the tail set for this second chaos functional x. Let us denote the variance of x to be sigma. And the variance can be bounded by k times n to the 1/2 minus 2h. Okay, so this is this can be obtained by a straightforward computation. It's a little long, but it's straightforward. You can get this bound. So let's normalize the x using the variation. We divide both x and m by sigma, and therefore x, the left-hand side, x over sigma is has mean 0 and variance equal to 1. And the right-hand side, we can write it out. It is m times n to the 2h minus 1/2. And now we are ready to apply the tail estimate for functionals in second chaos. So it's well known that for a functional in second chaos, we have the following bound for the tail. The probability that of the tail is less than k times e to the minus ka. Let's apply. So this will be our a right here. Let's apply this tail estimate. We get the bound e to the minus n to the 2h minus 1/2 times k times m. Okay, so this gives us a bound for the tail of x. And let me just rewrite this again. So this is just what we just got. And back to S3, we can sum up all the tail estimates, and we get a tail estimate for S3. And you see the terms in the summation is independent of the choice of the subset. So we just count the number of partitions, which is n choose m. Okay, so once we have the tail estimate for S3, let's get back to M3. And we can get a very simple bound for M3 by these two terms. And the exponent is S3. Here the G, we can choose it to be the P variation of B. Okay. Now, the P variation of B has a Gaussian tail. And so we can, so using the tail for S3, we can get this explicit bound. Remember, the maximum of S3 is n, so that's why the m runs from 0 to m. And we get this explicit bound. And now it becomes a calculus problem to show that this is bounded by a constant. Okay, so this is the integrability for M3. So let's put everything together. We have mentioned using the Borel's inequality, we can get the estimate for M0, and this is what the tail estimate looks like. k times e to the minus k times log a to the gamma. And gamma is a number between 1 and 2h plus 1. And on the other hand, we have just shown that both m1 and m2 are uniformly integrable. So we put this together, we get the bound we want for the Malliavin derivatives. Okay, I will stop here.
Thank you very much for this nice talk. Let's thank Yanghui for this talk.
Thank you.
Are there any questions? Maybe I start with a question. So can you go back to the slide where you mentioned the strong rates? So if I remember correctly, you said you need somehow that H is larger than 1/3. And
yeah,
I was wondering why you can't go down to 1/4.
Yeah, this is a...
Because the rate should, still be good if...
annoying. Yeah. So unfortunately, we only have 1/3. Yeah. So
okay.
Remember, you need to use. So in our approach, I used the BQ couple to be the driving process, and that approach doesn't work for H below 1/3. So
I see.
Yeah, and yeah. So in the same condition, I think it might fail. The convergence might fail. But if we assume stronger condition to the system, we might and in a different way, some new idea, we might be able to get the convergence. But so far we don't have the strong rate below 1/4, or below 1/3.
Further questions? Okay, then I have one more. So my question is, okay, so here you consider the situation where your system is driven by a single fractional Brownian motion, right?
Mm-hmm.
So what happens, are the results that you have shown us also applicable to the situation where your equation is driven not by a single fractional Brownian motion, but say two with different Hurst indices? So in general, you have D, processes, and they have maybe D different indices. Would that still work, or is that a problem?
Like a drifter?
No, so you have dB, and then you have dB prime, and so VYT dBT, and then plus say WYT dB prime T, where D prime is another fractional Brownian motion.
Okay, it's like a mixing of different H.
Yes, different H. Say one is Brownian motion and one is fractional Brownian motion. So you want to combine the semi-martingale case with, you want to add a fractional Brownian motion to the semi-martingale case. So that's my...
Yeah, that's a very interesting question. So my approach should work for also for mixing system, but I don't. I have no idea what's the rate should be.
Okay.
Yeah. I think for the system with mixing parameters, it shouldn't be too bad. So if I go back to this kind of decomposition, so in our paper in 2015, we have derived a general decomposition for any numerical scheme, which does not make any assumption on the driving process. So based on that decomposition, we can still get something about the mixing system. But
you will probably get some cross terms, right? With
mm-hmm.
one Brown emotion, and the other is the fractional one.
Yes. Yes.
Okay.
That could be very interesting. Yeah. So the problem will boil down to calculating the bound for weighted sum.
Yeah.
Which could be you know, little technical because you have several different parameters, different Hurst parameters. But if you if you are satisfied with, if you don't want to, you're satisfied with not the exact rate, then you can always think of them as the same regularity. You just pick the lowest regularity to be the,
I see. Yeah, sure. Yeah.
You can always get something, just think of them as the same regularity, picking the minimum of the regularity. Yeah.
Okay.
Yeah.
All right. Are there any further questions? Okay, so if not, let's thank Yanghui again.
Thank you.
And let me announce that the next SPDE seminar will be on March 12th, and we will have Markus Reis from Berlin speaking. Okay, thanks everyone. Bye.
Bye.